Now we will go for the next equation. So we know that the rate of change of momentum is equal to the negative gradient rate of change of potential. We know already the force is equal to minus dV minus del V. We know already this one. Negative gradient of potential which is equal to the force, we know already. So instead of force we can write dP by dt, Newton second law. Okay, F equal to dP by dt. So dP by dt which is equal to, instead of del V you can write dV by dx, gradient of field. So 1.80 is well known equation which you have studied earlier. Now corresponding expectation values. We'll go for corresponding expectation values. So the expectation value of momentum which is equal to minus expectation value of the gradient dV by dx. Is it clear? 1.81. And of course we know this equation, the expression of the momentum is given by this. Okay, so this we know already. So instead of P you can substitute the operator minus I h cross d psi by dx. Okay, so you can write this equation as psi star d psi by dx, pulling minus I h cross out, that will give you this equation 1.84. Okay, now this is P, but we need only dP by dt. Okay, P is given. Okay, so now we have the dP by dt. So differentiate on both sides with respect to time. So dP by dt will give you d by dt of this equation. Is it clear? D by dt of this equation. As usual, you will have to differentiate this with respect to time, keeping this as constant, plus keeping this as constant, you will have to differentiate this as usual. So we are going to do 1.85. We are going to differentiate with respect to t. So we will get d psi star by dt, d psi by dx plus psi star. So you will have to differentiate other term keeping psi star as constant. So psi star d by dt, d psi by dx, dx. Is it okay? This equation. Now x and t both are independent variables. Okay, x and t both are independent, so we can exchange. Doesn't matter. Dependent variable we can't exchange. Okay, so both are independent variables, so we can exchange. We can exchange the second term as here it is d by dt. We are going to exchange with x and here t. This term will be the same. We are going to exchange these two alone. Now as usual, we will have to use starting the time dependent equation. We will have to go with d psi by dt. Get the expression, we know d psi by dt. We will also come to know d psi star by dt. Substitute here and get the results for dP by dt. That's all. Okay, is it okay? So now as usual, this equation you will have to write 1 by I h cross d psi by dt is equal to 1 by I h cross. As usual, earlier we studied the same thing. Okay, multiply and divide by I, that will give you minus I by h cross, the same term. So d psi by dt will give you, multiply this term will give you this expression 1.91. Now take the complex conjugate, it will give you this. You are going to take the complex conjugate. Okay, is it okay? We have the same argument like last time. So d psi by dt. Now we are going to substitute. So this is the equation, correct? We are going to substitute d psi star by dt and d psi by dt. So this is the expression for d psi star by dt, and d psi by dx is here. Okay, plus psi star is here, d by dx, partial d by dx is here. D psi by dt is expression for d psi by dt. I have written the second term, which is equal to 1.93. Is it okay? Is it okay? This is the equation. We already got the expression for d psi by dt and d psi star by dt. You substitute. D psi star by dt is given by this expression. Your d psi by dx is here, plus psi star d by dx is here, and this expression is for d psi by dt. So substitute. Okay, now you are going to separate. This is kinetic energy part, this is potential energy part. Similarly, in the second relation, we have kinetic energy part, potential energy part. We will separate kinetic energy on one side, potential energy on another side. Okay, so now minus plus. So I h cross, you pull I h cross by 2m out. So this term I have written d squared psi star by dx squared partial and d psi by dx. Is it okay? Similarly, here kinetic energy part will be I h cross by 2m we have taken already out. Okay. So this minus sign, that plus, that will give you minus sign. So psi star d by dx and d squared psi by dx squared. So we have taken kinetic energy part on one side. Any doubt here? Any doubt? I repeat, you have minus minus plus, here I h cross is there, you have I h cross by 2m, I h cross by 2m, you pull it out. Remaining terms d squared psi star by dx squared, d psi by dx, so you have to multiply. So I have written here. In the second term, you have already the minus is there, so you have to go with one minus sign. Okay, minus here, so minus sign. So remaining term you can write psi star d by dx, partial d by dx. Already we have pulled I h cross by 2m out, so this will give you d squared psi by dx squared. So we have taken kinetic energy term out. Now we'll go for the potential energy term. So potential energy term minus I h cross is here. Okay, so minus I h cross. The remaining term will be your I h cross. Here also it's common, so you can pull it out I by h cross. So you have remaining term will be b psi star d psi by dx. Correct. We already pulled one minus sign out, so that will give you minus psi star dv psi by dx. Okay. Any doubt? So now I into I squared minus 1. So you have minus h bar square divided by 2m. This term, let it be like this. Okay, we have written the same thing, no problem. Now h cross h star will go off. I into I squared minus 1, so minus minus plus, so plus. The same term we have written. Any doubt? Any doubt? Same term. Now we write the same term here. The last term b psi is here. Okay, just differentiate with respect to x, because b also depends on x, psi also depends on x. Okay, so keep b as constant, you will have to differentiate, plus keeping this as constant, you will have to differentiate another one. Is it clear? You have to differentiate b and psi both. Keep b as constant, differentiate psi. Keep psi as constant, differentiate b. So you will get these two terms. Come on, psi star dv by dx psi. Okay, minus sign is there. Minus psi star. Keep b as constant, differentiate d psi by dx. The first term and last term will get cancelled. So you have only this term alone. Okay, so we will get only this term alone. Let it be. Okay, kinetic energy term, let it be like this. So we can write this minus sign inside, minus partial dv by dx. I am going to take this minus sign inside. The reason is dv by dx with a minus sign sandwiched between normal wave function and the complex wave function. Sandwiched between normal and the complex wave function. So this term is nothing but expectation value. Correct? Any expectation value can be written as sandwiched between, we discussed already, sandwiched between normal and complex wave function. So normal and complex wave function. Ordinary wave function and the complex wave function. So the second term can be written as like this. So we can replace the second term as the expectation value of potential energy. Okay, gradient. So this term, we have brought this term exactly same as it is. So this equation becomes this equation. Any doubt? 1.99. Very simple one. So now we are going to take the second term of the kinetic energy part. Okay, we are going to take the second term of the kinetic energy part. We are going to solve as usual using udv, that method. Okay, udv equals uv. Just take the second term. Second term is this one. See, second term is this one. So you are going to take this one. So just keep this as u, this as dv. When you are going to u dv, okay. So u dv you will get uv. U is this one, correct? V is one derivative will go off. So you will get d squared psi by dx squared. uv with the limit minus m to plus infinity. And you just argue the same argument. This will become 0. So this will be 0. And the second term will be minus v du. So minus v du. So v is this term alone. D by dx will go off. So this term alone. U is d psi star by dx. So d squared psi by dx squared d psi star by dx. Okay. For the second term. Already one minus is there. So minus minus plus. So we can replace the second term as this term. This is the first term. This is the second term. Correct. This is the second term with a minus sign. We have already found the relation. We will found the equation as minus. So minus minus plus. So this is equation. Okay. These two terms, we can write these two terms as like this. These two terms can be written as like this. For example, d by dx of d psi star by dx. So you just have this one. Okay. So I can write d psi star by dx. One plus is here. Okay. D psi by dx. You just differentiate this, keeping this as constant. So d psi by dx. This is 1 plus is here. Okay. Don't forget 1 plus is here. Now you differentiate this, you will get this d psi by dx plus you differentiate this, keeping this as constant. Is it okay? What I am saying? You have to differentiate this. See, what does it mean? Keeping this as constant, you have to differentiate. Then next time, keeping this as constant, you have to differentiate this. You will get this. Okay. This is not plus sign. It is correct only. It's correct. UV. You have to differentiate this equation. There's no plus here. You have to differentiate these two. Okay. So when you are going to differentiate this, keep this as constant. You have to differentiate. Plus keep this as constant. You have to differentiate this. Is it okay? You will get this term. So this term can be replaced by this term. Is it okay? These two terms can be replaced by this term. I'll do it once again. See, this term can be written as exactly like this. Because when you are going to differentiate this term, you have to differentiate this, keeping this as a constant. Plus, keeping this as constant, you have to differentiate this. Okay? So this is what we'll have to do for UV method. So keep this as constant. You will have to differentiate this. You will get this. Keep this as constant. You will have to differentiate another one. You will get. See, this is constant. You will have d squared psi by dx squared. Now this integration is there. D by dx with respect to dx. This dx and dx will go off. Okay. Integration differentiation will get cancelled. D by dx. So you will get dx. That dx will go off. The integration differentiation will go off. You will get the limits. Straight away you can have the limits. You substitute the limit. Is it okay? Clear? Shall I repeat? See here, dx and dx will go off. This integration differentiation, okay, will get cancelled. Correct? So straight away you can substitute the limit. And of course we know the limit minus into plus infinity. Not only the wave function but also derivative also will be 0. So this term will become 0. So left hand side you have dp by dt right from the beginning. So the expression value of dp by dt will give you minus dv by dx, which is nothing but your f. Okay. So this is the equation of motion. So this equation is exactly equivalent to the equation of classical mechanics with the expression value of p playing the role of momentum of the particle. So this is similar to the Newton's second law of motion, which has been derived from Schrödinger time dependent equation. So we have derived from Schrödinger time dependent equation. We have obtained the Newton's second law of motion. Okay. So for everything you will have to derive. Suppose we want to find out the classical mechanics, a new thing, then you will have to explain in terms of classical mechanics. So classical mechanics is the base. It's a base for everything. Suppose if you are finding a new idea in statistical mechanics, in thermal physics, in electromagnetic theory, you will have to derive in terms of quantum theory. Only then the theory will be accepted. Because quantum theory is the base. Okay, base for everything. So we can say that, right away we can say that quantum mechanics is the parent. Okay. One child is classical mechanics. Another child is thermal physics. Another child is statistical mechanics and so on. So quantum mechanics is the parent. Okay, over 100 years, 120 years only, scientists have discovered quantum mechanics. Whereas in classical mechanics, we have studied right from 400 years. Okay, but we should say here, right away here, that classical mechanics is the approximation of quantum mechanics, but not on the other way around. Okay, so hence we can conclude that the quantum mechanics corresponds to classical mechanics in the limit that spatial extent of the wave function, which is typically of the order of de Broglie wavelength, is negligible. So if you have a size which is exactly equivalent to the de Broglie wavelength, then quantum mechanics exists. The result we can obtain. See, for example, de Broglie says that this particle also will have wavelength. I have also wavelength. Okay, myself, I have wavelength. I can say that this is very small. Very small. That's the reason. It is not exactly comparable with the de Broglie wavelength. Size is not comparable with the de Broglie wavelength. Okay, that's the reason. So this is an important result because we know that classical mechanics gives the correct answer in this limit. Thus the wave packet moves like a classical particle, and the expectation values are the real values in mechanics, classical mechanics. Thus the rate of change of momentum is equal to force, which is Newton's second law of motion, which we have already seen. Okay, it states that Schrödinger equation leads to the classical Newton's law of motion on the average expectation value. For the large quantum numbers, classical and quantum mechanics give the same results. Okay, large quantum numbers. Not only large quantum numbers, lambda tends to 0, h tends to 0, we will get the results of classical mechanics. This reduction of quantum mechanical dynamics to the classical trajectory is known as Ehrenfest theorem. So those two theorems are Ehrenfest theorems. Okay. Now you could have asked this question: why should we always go for the momentum operator as minus IH cross del? Why can't we go with P equals plus IH cross del? You could have asked yourself, correct? Of course, E equals IH cross partial d by dt. Plus is there. Some satisfaction. But here, P equals minus IH cross del. Correct? So this is the way that you could have asked yourself earlier. You didn't ask me, but you could have asked yourself. P equals minus IH cross del. What is the reason? The slide clearly says that P should be minus IH cross partial d by dx. Suppose if P equals plus IH cross del. Suppose we think. Suppose if you are going to keep P equals plus IH cross del, then you will get the answer as dp by dt equals minus f, which doesn't exist. It has no meaning at all. So that's the reason P will have always minus IH cross del. Is it okay? Suppose if P equals IH cross del, you will get F equals minus dp by dt. Okay, F equals minus dp by dt, which is wrong, which is meaningless. That's the reason that always P equals minus IH cross del. So this slide says that P, the momentum operator P equals minus IH cross del. So that is the end of